Hi, hey everybody, welcome. Good to see everybody. Don't know if you missed me as much as I missed you over the break, but it's good to have you back. I hope you guys enjoyed it, got some rest over the past week, and we're in the home stretch. So I guess that's the nice thing about having spring break so late. So I posted an announcement this morning about kind of the work that's left for the rest of the semester, which is not too much. Yes, that's right. Getting there. So we've got one more homework assignment, which is due after next week. So it's due Thursday of next week. One more reading quiz on Wednesday. No reading quizzes for next week. And then we've got our exam number 3, which is 2 weeks from today. So that's May 10th at this time. So exam 3 is not a final. It focuses on what we've done since the last exam. So that's chapters 6, 7, and 8 in the text. So that's the plan for the rest of the semester. So we're going to just finish up chapter 8 is the plan. So we'll go through some new stuff today and Wednesday and Monday. And then on Wednesday of next week, we can just use that time to get ready for the exam or go over homework questions that you might have on that. So any questions about that before we get started? I don't know if you guys are getting a lot of noise from outside, but if you are, just let me know and I can close my window. I want to also just point out some stuff on our website. This is a different course. Here we are. So one thing is I added some links. I added a module here just with YouTube playlists. These are up on my YouTube channel. These are different than the Zoom. It's the same content, really similar. We go through the same problems, but these are like mini recorded lectures without an audience at that time. So it's just me talking to a screen. So if you find those useful, they're just different types of videos. Feel free to use those. So the test is on these chapters over here. And I also put something in the announcement about FCQs. So FCQs are our course evaluation. They are open as of today and they stay open for a week. So FCQs are really valuable for us. So your feedback is really important. So don't think that we don't care about what you say. We actually value it quite a bit. It goes into our own merit evaluations about how we are doing as instructors. So your comments are very much valued by myself and by our department. So please do take the time to fill those out carefully. I appreciate your feedback. And if we get 80% of the class or above that responds to that, then we'll get extra points, 2 bonus points for your cooperation on exam 3. So I'll just be kind of pestering you about this week if we're not getting responses in. But please, take some time to complete those evaluations for all of your courses. Okay, so yeah, so the plan today is to just keep on working with hypothesis tests. And what you guys had to do on the reading assignment was basically refresh your memory about what we did before spring break. So that was doing a test on a single mean when, in that case, we didn't know what the population standard deviation was. So what I want to talk about today is how we do tests when we're comparing 2 populations. A hypothesis test is this mean different from that mean type of stuff. So we were doing single means and single proportions last time. So before we get started, the process for these tests are the same in that, it's kind of a step 1, state the hypotheses. Step 2 is kind of collect your sample data. Then based on that sample, you compute a test statistic. And then from that, you find the p-value. And then compare to the significance level. And I'll just say, this we've been working on, so that hasn't changed from when we did permutation test earlier in the semester. Okay, this part over here, you're not doing your own analysis here, so you won't have to collect data, but you'll be using the sample data to collect the test statistic. So this was new. We worked on that last time. We talked about how we can go through that process using central limit theorem as opposed to simulation-based methods. So let's just kind of do some light stretching after spring break. Don't want anyone to get hurt doing too much statistics too quickly. So I want you guys to just let me know for each of these hypotheses, whether they seem valid or not. I'm trying to find my poll. Here it is. So the question here is relating to A. So in A, we've got these two competing hypotheses. Mu is 50 versus mu is greater than 50. So the question is, are the hypotheses valid? So either they're both fine, one of them is wrong, both of them is wrong. Okay, so here were the results in case you're curious. So we had 5 out of 6 say they're both fine and 1 vote for an incorrect. So these are both fine. We've got just the things you would want to keep in mind is we're using mu here. We're using population parameters, which are good. Our null hypothesis has an equal sign. And our alternative hypothesis has a not equal to some inequality, in this case, a greater than. So this all works out fine. These are some of the things we would want to keep in mind when we're doing this. That when we state these hypotheses, we use population parameters, mu, and not sample statistics, x bar. We use x bar to find the test statistic. Again, these are some rules that we would want to keep in mind here. Good. So in that case, this is fine. And we're also asked here to think about whether this is a one-tailed test or a two-tailed test. And in this case, this is a one-tailed test. And in fact, it's a right-tail test, right, because of the greater than sign. And then the process that we lined out last time is what would I do with all this information? We think about the sampling distribution for x bar in this case. And we would set up our sampling distribution is going to be centered at the claim in the null hypothesis. We collect some sample. Our sample has some mean, and then the p-value, right, would be this area over here. So that's why we call it a right tail test, is because we're calculating area in the right tail. Any questions? Okay, so let's try this again with B. What do you think about B? So here we've got a lot of people said that they are both not correct. And in this case, that's right. In order to fix this problem, if we flip them around, which is what's done in D, essentially, actually D is slightly different, but if we flip these hypotheses around, they would work. But these are reversed. So for the null hypothesis, we should have an equal sign. And for the alternative, we should have one of these signs over here. So these, it seems like these hypotheses were flipped around. But in any case, if the question is, are these valid? No, they're both incorrect. Probably they need to be switched. Okay, let's give C a shot here. I don't know how the math works out here. We have 7 people that are out of 6 that voted on this, but that's okay. That's a glitch in Zoom, I suppose. But there were 7 people here. Most said that they were both wrong. And the problem here is similar to the top one in that these are probably switched around. The null hypothesis should have an equal to sign, and the alternative should have a not equal to or less than or greater than. Okay, in the chat, tell me which of them are valid. I'll set it up so that the chats come to me. You don't need to chat to everyone. Okay, so I'm looking through the responses here. Everybody said that D was valid, and it is. So D is a valid one. Okay, we've been stating them like PA minus PB equals 0, but this is equivalent to doing it that way. And here we've got a two-tailed test. Let's see, looking at the responses that came in, I would say about half the people said that E was okay, and the other half said that E was not okay. So this one is not valid. Does anyone see what the problem is with this one?
You're using sample statistics instead of population factors.
Sorry, what was that?
You're using test statistics.
That's right. Thank you. That's right. So here, notice we're using X bar in these claims. These should always be stated using population parameters. So we want to use mu, not X bar. We want to use P and not P hat as well. If you wanted to state these claims correctly, it should look something like that. So just remember that. I think everybody said F was good. Just about everybody got F. No, let me change that. I'd say this one is about 50-50 as well. And this one is no. Although it satisfies both of these things that we described below, we're using P, that's great. We've got the right equal signs and inequality signs. What's the problem with this one?
The values are different.
That's right. We have 0.25 and a 0.5 over here. So these should be directly competing claims. There shouldn't be any gray area in between them. So these numbers have to be the same over here and over here. So we can add that to our list down below. That we're using different inequality symbols, but we're using the same values. And so that is indeed fixed in G. They changed that 0.5 to a 0.25, and now this becomes a valid set of hypotheses, and it becomes a right-tailed test. Okay, let's see. Yeah, I think there was a question that came in about F, but I don't know if I answered that. So F is not valid because we've got those two different values here. Okay, any other questions? Okay, so we spent some time on that because that is the, you want to get step one right, or else you're going to go off in the wrong direction. So yeah, we're stating these are claims about population parameters. And now I just want to kind of summarize the process in general before we start to do like, here's a difference of means, here's a difference in portions. And I don't want you to think about this process as being different in all of these different situations. We're doing the same thing in all of them. And that is right. We have a null hypothesis, which is going to be population parameter, or maybe parameters, if there's more than one, are equal to some fixed number. And HA is going to be that population parameter, or if we're doing a difference of parameters, is not equal to, greater than, or less than that same number. And based on our hypotheses, we set up a sampling distribution for the test statistic. Okay, by thinking about the following thing. The formula for the test statistic, there's really just one formula, and I want to make sure you guys have this in mind before we start to think about different special cases. And that is, we're going to take our observed sample statistic and we're going to see how far is my observed statistic from the null claim. And then we want to describe that distance in terms of how many standard errors away are they from each other. And so we divide that by the standard error. So the test statistic is saying how many standard errors is our observed sample from the null claim. And we do this the same way in all of these cases. Just what changes is how we calculate the standard error is going to be different whether we have means or proportions, difference of two means, difference of two proportions. And so last time we were doing things with single means, and in that case, the standard error was depending on whether we knew the population standard deviation, either S over the square root of n or sigma over the square root of n. We did not use this process for a single proportion. We used binomial distribution for a single proportion. Any questions? Okay, so now let's kind of think about how we calculate the standard error in these different situations. So when we're going to do each of these, similar to the way we did confidence intervals and these tests last time, is there's kind of showing your steps along the way and calculating the test statistic. I say by hand, but really what I mean is like by step. We're using a calculator, but we're calculating the test statistic and then calculating the p-value. Or we can use these built-in functions in our the t-test function, the prop test function. And these functions, they do the work for us and they tell us what the p-value is. So on your homework assignment, I ask you to do some of these in different ways. So just pay attention to that. So we'll think about how we could do it for both of those. So for a difference in two means, we have already talked about how we can get the standard error for that sampling distribution. So let me just come back over here. If we have a difference in two means, then that standard error formula looks like this. But otherwise, we're using the same formula for that. And again, we have this distinction as far as if we know the population variances or not. And I'll say, usually we don't. So usually we're in this situation. So in addition to thinking about whether we know S or sigma, that also is going to affect how we calculate the p-value. So just keep that in mind. Okay, excuse me, I have something in my throat. Okay, so before we worry about this stuff over here, let's kind of just think about how we could do this, what I say by hand here, but kind of going through the steps. So here what we've got is somebody is wanting to test a claim and they want to see whether there is evidence that female nurses earn less than male nurses. Okay, so I'm going to, first of all, looking, excuse me, at the statement above, and we've got males, we've got females, so we're comparing two different populations. We don't have matched pairs here. And we're going to compare salaries of these two groups by comparing their means. So I'm going to state my null hypothesis as saying there is no difference between the amount that males and females make. Their means are equal to each other. And in this case, we have a one-tailed test because they want to see in particular if they suspect that females make less. And so if females are earning less than males on average, then this difference, right, would be negative would be positive if that were the case, right? If females are making less than males, then the mu sub m would be bigger than mu sub f. And you could state this as mu sub f minus mu sub m and get equivalent sort of statements. Kind of paraphrasing what this would be in words, you could probably express that a little bit more clearly. But here we're saying male nurses on average earn more than female nurses. So when I'm figuring out what my hypotheses are, it's really just that line that I've highlighted in yellow that I need. All the rest of this stuff is going to go into calculating the test statistic, but I don't need that information to state my hypotheses. Okay, and then we see here, this is the stuff that's going to be useful for calculating the test statistic. So we've got some information about the women that I've highlighted in purple, and then in blue for the men over here. And so notice in particular, we don't know what the values for sigma 1 and sigma 2 are. And that's really important to pay attention to before you go deeper into the problem. Okay, we're given sample standard deviations, not the population. So the test statistic is going to take what is the corresponding statistic that I get from my sample for the difference. So that's what the x bar m minus x bar f is. So this is like my observed sample, and this is the null claim. We don't need to put this 0 here, but I'm going to leave it here just as a placeholder. So the 0 over here comes from this claim over here. So we're going to compare the difference I got from my sample versus the claim in the null hypothesis, which is that the difference should be 0. So I'll just say that's why there's no 0 over here, but you could think about it like this, and this makes it look closer to observed sample minus the claim over the standard error. So I kind of think of this as two separate calculations. I calculate the standard error and then plug it into the formula. So let's see. In this case, the standard error, right, would be the square root of the standard deviation for the men, which is 300 squared, over the sample size for the males, which was 16. And then we have for the females, the standard deviation was 250. We square that and divide it by the sample size for the women. And we take the square root of all of that. So if you've got R handy, you might want to just check these calculations to make sure you're getting the same thing as me. So I'm getting like about 93.5. And then once we have this, we can then say the mean for the males was 23,900. The mean for the females was 23,750. So it seems like they're kind of close. And then we would divide that by 93.54143. And this comes out to approximately 1.604. So that would be our test statistic at least. So when I say do it by hand, that's really what I mean is like, show me what the standard error is and then calculate the test statistic. You don't need to take the square root by hand. Use a calculator for that. Okay, so if there aren't any questions about the test statistic, and please don't hesitate to ask. Then when we want to find the p-value, again, since we did not know the variances here, we're going to use a t-distribution. And we can use this really formal Welch's approximation. But when we're kind of doing this thing, you know, what I'm saying by hand, we can just calculate the degrees of freedom by taking the smaller of the two samples, which in this case is the 16 men, and subtract 1 from it. So we're going to use a t-distribution with 15 degrees of freedom. And what we've got is this t-distribution. It's centered at 0, and we got a test statistic of 1.604. So our p-value would be the area to the right of 1.604 under this t-distribution. So remember, the PT function is like the P norm type of function, except for a t-distribution. So the first argument is the test statistic that we calculated, and the second argument is the degrees of freedom. And what comes out of this would actually be all of this stuff over here. And we want the area on the other side. So we subtract 1 from it in order to get the stuff in green. And let me double check that. So here, the p-value is approximately 0.065. I'll take it out to here. Questions? So, you know, just make sure you make a note to yourself that we used t distribution here, not a normal distribution, because we did not know what the values for the sigmas were. We approximated them with the corresponding standard deviations from the sample. And I received a question in the chat as far as like here, we subtracted this value from 1 to get the area on the right. Yeah, there is a option in the P norm and in the PT function in R, this PT command, where you could add like a lower tail equals false, and that gives you the stuff to the right. So that would work too. Yeah. Okay, so we've got our p-value. That's telling me how much area is over here. And now let me open up the a poll for this. So what would the conclusion of this test be now that we've got the p-value and we're testing this at a 5% significance level? All right, thanks for those responses. So we had 5 people respond here. 4 said we would fail to reject the null, and 1 said we would reject the null and accept the alternative. No one chose the middle option, which is good, because that's never going to be a possible conclusion. So the possibilities would be either the top one or the bottom one. And remember that if the p-value is bigger than the significance level, which is the case here, we fail to reject HO and the test is inconclusive. So we really couldn't say anything one way or the other about salaries. This doesn't tell us that they make the same amount of money. It just tells us that this data doesn't give us a definitive answer one way or the other. Okay, any questions about that? So just so you know, like on the homework that is due next week, you know, you're gonna have to do some tests for a mean, for a proportion, difference of means, difference in proportions. So just pay attention to what type of test you want to use. And we're gonna kind of just go through one example together for each of them. No final thoughts or questions about testing differences of two independent means. We didn't do matched pairs. Okay. So next up is doing a difference in two proportions. And this becomes a little bit trickier because we have a formula for the standard error for a sampling distribution for a difference of two proportions. And that formula depends on, let me just say, that these formulas look like this when we did central limit theorem for a difference of two proportions. And the problem is when we're doing hypothesis tests, we don't know what the value for P1 is, and we don't know what the value for P2 is. There's no claim being made about individually the value of P1 or individually the value of P2. The claim is these two values are the same. So we can't really use this formula over here because we don't know what this is or that or that. But again, we want to set up these sampling distributions assuming the null hypothesis is true. And the null hypothesis is always going to say that the difference of these two proportions is 0. Right? So that's the way these hypotheses go, or at least the null hypothesis goes in this case. So the way that we're going to set up this sampling distribution, the way we're going to get our test statistic is by assuming P1 and P2 are the same. And I'm going to assume that they're both equal to what we're going to call the pooled proportion here. So what I'm going to do is I'm going to group these two groups together and just think out of all of the people in both of these groups combined, N1 and N2, what were the total number of successes of both of those groups combined? And that's going to be the pooled proportion. So when we calculate the test statistic, right? We kind of do the same thing. We take our observed sample difference, the difference in sample 1 proportion and sample 2 proportion, right? And we are thinking about this as the observed, and we're subtracting the null claim. And since the null claim is that the difference is 0, right, we actually can just write this up top. And down below is the standard error. So the standard error depends on this pooled proportion that we find over here. So that's what this P sub P is referring to. And when we calculate the p-value from this, we're gonna not use a t-distribution, but we're using normal distributions with proportions. Whenever we're working with a proportion, a difference of proportions is always gonna be a normal distribution. So when we're doing a difference in proportions here, we have a different standard error formula, but the test statistic is going to be the same once we have that standard error. And we're going to use a normal distribution to find the p-value. So exactly what we're doing is we're using the same formula that we have for the standard error for sampling distribution for difference in proportions. And what we're using in place of the P1 and the P2 in those formulas is the pooled proportion. So in each of these places where we had the orange thing, we're instead using the pooled proportion of the sample. And that's where this formula for the standard error comes from. And I realized that when we did this example, we didn't use the t-test method in R. And in fact, we couldn't do it for this example because we don't have the raw data. But we'll take a look at how this function does work with some other examples. Okay, so let's take a look at this example. And I think the best way to kind of get a sense of how these formulas work is to just do some of these calculations. So here the problem is there's an artificial sweetener that actually has been linked to decreasing the frequency of ear infections in children. So it's called xylitol. And so researchers believed that the proportion of ear infections in a placebo group, meaning a group that didn't get this artificial sweetener, is going to be greater than the proportion of infections in the treatment group. We'll call the group that got the sweetener the treatment group. So we're going to call the xylitol group the treatment and the placebo group the control. So remember, placebo means they were given something, just a pill that has no active ingredient in it. So in this case, they are claiming that the placebo group is going to have a greater proportion of ear infections which would make this difference in proportions negative. So we expect the P from the treatment group to be smaller than the P from the control group if this ingredient is in fact having some effect on ear infections. Questions about the hypotheses? Okay, so then when we calculate the test statistic, we're going to need to figure out what the pooled proportion is. So let's do that first. Okay, so really what the pooled proportion is saying is let's group the control group and the treatment group together. So we had let's see, the number in the treatment group was 159 and the control group had 165. And we had 46 ear infections in the treatment group and 68 in the placebo in the control group. So this comes out to approximately 0.3519. Okay, so what this is telling me is out of all of the people in the survey, in this study, 35% of them got an ear infection. Whereas if I were to look at just the treatment group, that would be 46 out of 159. Which is about 29%. And then we had the control group, which had 68 out of 165. And again, since the null hypothesis is claiming that these two proportions should be the same, when we calculate the standard error, we're going to assume that those proportions are the same. And so the logical choice for what those things would be the pooled proportion. So we've got these three different proportions. Just be sure you keep them all distinct, right? One is just the treatment, one is just the control, and the pooled is when we group them both together. And so now when we do the standard error, we're going to take the pooled proportion times 1 minus the pooled proportion and we get this big calculation over here. And don't underestimate these calculations. It's real easy to misenter something. So just be sure you're doing this carefully. I would recommend using R. And I would also recommend trying to do this calculation right now just to make sure it's working right. I have not done it myself. And I got this about 0.0531. that match up? Good, thanks, Jonathan. And then from that, we calculate the test statistic, which we now use Z to denote that, because what we're really finding is the Z score of our sample difference. So we're going to use a normal distribution here. So now I would plug in the 0.2893 minus the 0.4121 and divide all of that by the 0.0531. So that's taking a look at, this was my observed difference. How far is this from the claim that it should be 0 in terms of how many standard errors is this? And let's see, I think that comes out to like 2.31. For the test statistic. It should be a negative, right? Sorry. Because I did my difference in treatment minus control. Okay, and now because our alternative had a less than sign, we would go to the left. We use the left tail test. So in this case, we could calculate the p-value using p-norm, right, which takes in z-score, and then we're using the standard normal distribution here. And for my p-value, I got 0.0104. Any questions? That's what like showing by hand means here's the standard error, here's the test statistic, here's the p-value, kind of showing those intermediate steps. We can use this prop test function to calculate this for us in this case. And so the prop test works like this. Similar to the other one, we're not including a confidence level. We're not putting that $conf at the end because we don't want a confidence interval. We want to do a hypothesis test. And this alt command here is telling us what is the alternative hypothesis. And so if you're doing a left tail test, then blah, what I have there as blah, is going to be less. If you're doing a right tail test, then blah would be greater. So basically, you're just describing what is the inequality I used in my alternative hypothesis. And if you're doing the two-tailed test, then you don't need to put that argument there. The default is that it's going to do a two-tailed test. So for us, we could go ahead and run prop test. And first we enter coordinates of the successes. So my first group was treatment, and that had a total of 46 successes. And my next group was the control. They had 68 successes. Here, success means ear infection. So it's a bad thing, but that's how we're thinking about it. And then we include how large each of those samples were. And you want to pay attention to the ordering here, right? Order them appropriately. And in this case, we do need this alt argument because we have a left tail test. So we're going to put that in double quotes, and that's going to calculate our p-value. And I'll change over to R just to show you what the output looks like. And so these are situations where you can pretty much just use the console down here to do these calculations, since they're not like for loops. We're not doing like multi-line stuff like we did with the simulation. So here I could just enter on this line prop test. What do we have? 46, 68. And we had
159 and
159
165.
and 165. And now we have alt is equal to less. And you can see, right, I'm getting this dialog box that pops up when I start typing something that doesn't make sense, for it to like fill in, these are the options. So I suppose you're supposed to write out alternative, just typing alt works. And if you do want to put a two-sided test, you could put two-sided in quotes. But again, if you just leave this argument out, the default is it's going to do a two-tail test. I want less for that. And that's it. So now when I run this, this was the output that I got. And so it's a lot of stuff. And so you just want to be sure you keep out, look out for what you're interested in. You can see here, it actually tells me what a 95% confidence interval is if I were curious. This confirmed what we calculated by hand, what the individual sample proportions were, but what I really want here is the p-value. So when we do this calculation, we got something a little bit different because it's using a slightly different test here, but it's pretty close to what we got. Yeah. So any questions? And I think it's good practice, you know, doing the calculations like we did first and then checking them in R. And then if we wanted to make a decision, and we're going to make this decision using a 1% significance level, what would be the conclusion in this case? Great. That was quick. Good. Okay. Failed to reject. That's right. Because our p-value in this case is bigger than the significance level. If we were doing this at a 5% significance level, then we would have enough evidence to reject the null hypothesis. That when we're working with proportions, you might recall that when we're using central limit theorem, when we're using a normal distribution to estimate things that are discrete, like how many people, how many children got ear infections, that if we're going to use central limit theorem, we might be safer to use a continuity correction. And so what that would look like here is that we would add or subtract 1/2 from each success count. So this is going to make these differences in proportions become closer to 0. And maybe this will explain why our, the p-values in the previous one were off, because we used the central limit theorem without the continuity correction. So that's why we got something a little bit different than what the prop test was telling us. Not going to ask you guys about this on the homework or on the exam. I'm totally happy with you guys using the prop test or not worrying about the continuity correction. But if you're curious about doing it, I don't want to like overwhelm you with 5 different ways of doing the same problem, because we're kind of splitting hairs. But I'll put up a solution if you're curious about how to use the continuity correction. And then what you'll see is the value that we get should be closer to what we got in our compared to what we got when we didn't use the continuity correction. So when we use the continuity correction, we should get a p-value which is a little bit closer to that. I want to do one last example maybe together where we're going to use R to do the t-test for us kind of all at once. We didn't use that t-test function. We can only use t-test if we have the raw data. When we were doing this example 3 with the male and female nurses, we didn't have the data set. We just had a summary of the data set. And so when we just have the summary statistics, all we can do is use the formulas. In cases like this, when we actually do have the raw data, then yeah, this t-test in R is nice because it does all of the calculations. Calculate sample means, sample standard deviations, standard error, boom, it does everything all at once. So I want to just show how that works in a case like this. So here's this North Carolina data set that hopefully you recall. And what these researchers are curious here, they're thinking about the weights of babies that are born to mothers that are smokers versus not smokers. So the alternative would be that the mean weights for the for mothers who smoke minus the mean weights for mothers who are non-smokers doesn't make a difference. And in this case, the alternative is just there is some difference. We're not claiming one is bigger or smaller than the other, just they're different. And so if I'm going to do this in R, right, remember, we would need to load the resample data set because that's where new North Carolina births 2004 lives. And then so we're going to do t-test here. And the variable that we're interested in this case, right, is we're comparing the mean weights. What are we taking the mean of? We're taking the mean of the weights. So the first thing is the name of the numerical variable that we're calculating the mean of. And in this data set, that was called weight. And then it's going to be a categorical variable that we're using to how we're splitting the groups. And the variable in the data set, whether or not the mother was smoking, is called tobacco. And that's yes or no. So this is going to be categorical. So we have weight, and then we're going to use this tilde. So this is telling us we're going to split the weights. We're going to calculate the mean weights differently based on the tobacco grouping. And then we need to tell what is the name of the data set, which is NC births 2004, and possibly describe what sort of test we want, one tail, two tail, whether it's left, right, or two tail. And since this is a two tail test, we don't even need to bother with that. So you do need to make sure you load that resample data package. That's all I need. And you can see here what they do is they do a Welch true sample t-test. So they do it very similar to the way we do it by hand, just instead of picking degrees of freedom to be the smaller sample -1, they're using a better approximation for the degrees of freedom. But otherwise, it comes out the same. And when you see something like this, this is scientific notation. This was the output that we got in R. This is the same thing as 6.08 times 10 to the -5th. So in other words, 0.0000608. And so we don't have a significance level given to us, but this would be just about any significance level. So if we were using like a 5% significance level, since it's less than that significance level here, we could say we have evidence for the alternative, which isn't saying that one is bigger than the other, just that the weights are different. Okay, so we'll stop here. I think really the only thing that's left to talk about when it comes to hypothesis testing is what to do for matched pairs. Otherwise, we've done differences in means and proportions. So what I want to talk about next time is we'll talk about what we do for paired ones, and then I want to talk about what happens when we make mistakes. How can we control for that, and those sorts of things. So some of the finer details of hypothesis testing, but we've gotten through kind of the big picture at this point. Okay, well, thanks everybody. So don't forget that before we come to class on Wednesday, you've got your last reading quiz, which is due before class on Wednesday. Homework, the last homework assignment is open. Feel free to get going on that. And please get your FCQ evaluations in. I would greatly appreciate that. Otherwise, I hope you guys are all doing well, getting down to the end of this semester. So that's good. I tried to pace it a little bit faster at the start of the semester, so we don't have too much to get through at this point. We've gotten through most of it, so we can take it slow and digest it. But okay, well, thanks everyone. Have a nice afternoon, and I will see you on Wednesday.